When you look up at the night sky, past the clouds and the shimmering stars, what do you see? You might see darkness, a vast and silent emptiness. But what if I told you that emptiness is an illusion? What if the space between stars, between galaxies, is actually a hidden ocean, teeming with invisible rivers of energy? This isn't science fiction. This is the reality of our universe, and it's powered by something you might not have even heard of: plasma. We all learn about the three states of matter in school, right? Solid, liquid, and gas. But what about the fourth state? It turns out that more than 99% of all the visible matter in the entire cosmos is unsolid, liquid, or gas. It's plasma. Think of it as a super-energized soup of charged particles. It's the very stuff that stars are made of. It's the fuel for the brilliant solar flares that erupt from our sun, the cause of the beautiful dancing auroras here on Earth. This electric lifeblood of the universe forms a cosmic web, a hidden skeleton of energy filaments connecting everything. Plasma shapes the magnetic fields that guide galaxies, powers the most magnificent explosions in the cosmos, and dictates the invisible architecture of space itself. For centuries, this fundamental truth was completely hidden from us. Ancient astronomers imagined the heavens were filled with a mysterious substance they called the ether, a medium for light to travel through. While the idea of the ether was eventually debunked, science discovered something far more incredible in its place: an electric universe woven together by the forces of plasma. It's an environment where charged particles and electromagnetic fields are constantly interacting, creating a dynamic, living cosmos. So, how did this fourth state come to be? Its story begins in the unimaginable heat of the Big Bang. In those first fiery moments, the entire universe was nothing but a sea of plasma. As the cosmos expanded and cooled, some of that plasma condensed into the gases, liquids, and solids we're familiar with today. But most of it remained, becoming the dominant state of matter in the vast expanse of space. Every time you see a flash of lightning, you're witnessing plasma right here on Earth. The glowing neon signs that light up our cities, that's plasma, a powerful arc in a welder's torch. Plasma, it's been here all along, but we've only just begun to understand its true significance on a cosmic scale. The solar wind, a constant stream of plasma flowing from the sun, travels across our solar system at over 1,000,000 miles per hour. When this cosmic river slams into Earth's magnetic field, it creates the spectacular light show we call the aurora borealis in Australis. These beautiful, shimmering curtains of green and purple light are a direct, visible connection between our planet and the plasma-filled ocean of space. Understanding plasma isn't just about admiring pretty lights, though. It's crucial for our future. Solar storms, which are massive eruptions of plasma from the sun, can disrupt our satellites, power grids, and communication systems. By studying plasma physics, we can learn to predict these storms and protect our technology. Even more exciting, scientists are learning how to harness the power of plasma. They're developing new forms of spacecraft propulsion like plasma thrusters that could one day carry us to Mars and beyond, faster than ever before. Here on Earth, researchers are working tirelessly to create fusion reactors, miniature stars, in a magnetic bottle that use plasma to generate clean, virtually limitless energy. Taming plasma could literally solve our energy crisis and unlock a new era of human exploration. So, the next time you gaze at the night sky, remember what you're really looking at. It's not an empty void. It's a vast, hidden ocean of plasma. A universe that isn't silent, but hums with energy. It doesn't just sit there. It flickers. It glows. It lives. This is the story of the electric universe, and we are just beginning to navigate its currents. Travel back with me, 13.8 billion years. The universe ignites not with a bang of matter, but as a maelstrom of pure energy. Temperatures soar beyond 1,000,000,000,000 degrees, a cosmic furnace so hot that atoms, the building blocks of everything we know, cannot exist. In this primordial chaos, space itself is a blinding fog, a dense, swirling plasma of fundamental particles, helitrons, protons, and photons colliding in a furious, high-energy dance. This was the dawn of existence, a time when the entire universe was a single, vast plasma cloud. So what exactly is plasma? We all learn about solids, liquids, and gases in school. Well, plasma is often called the fourth state of matter. Imagine taking a gas and heating it up, and up, and up, until it becomes so incredibly hot that its atoms are literally torn apart. The electrons are stripped away from their atomic nuclei, creating a sea of charged particles, positively charged ions, and free-floating electrons, all moving independently. Because these particles carry an electric charge, plasma doesn't behave like a normal gas. It's alive. It responds to electric and magnetic fields, can twist and flow, form intricate filaments, and generate powerful electromagnetic waves. Unlike a neutral gas, which just drifts along, plasma is dynamic, constantly interacting with itself and with the invisible magnetic fields that thread through space. For about 380,000 years after the Big Bang, this plasma fog dominated everything. Then, as the universe expanded, it cooled. Eventually, it became cool enough for those free electrons and protons to finally find each other and combine, forming the first neutral hydrogen atoms. This pivotal moment, known as recombination, marked the end of the universe's first plasma phase. Suddenly, the cosmic fog cleared. For the first time, light could travel freely across the cosmos without being instantly scattered. And that ancient light, it's still traveling today. You see it as the cosmic microwave background radiation, a faint, ghostly glow across the entire sky, direct echo of the plasma universe. But even as atoms formed and the universe became transparent, plasma didn't disappear. It just withdrew. It became confined, tucked away inside the fiery hearts of stars, woven into the fabric of galaxies, and trapped within vast magnetic structures that continued to shape the cosmos on every scale imaginable. It was waiting for its next act, and that act began when the first stars ignited. Their intense radiation blasted the surrounding gas, ionizing it and creating massive bubbles of plasma once more. Exploding stars, supernova, and high-energy cosmic rays filled the space between stars with charged particles. Galaxies evolved into intricate webs of plasma, threaded by magnetic fields so complex that even today, we're just beginning to unravel their mysteries. Today we are swimming in a plasma ocean. The seemingly empty space between planets is filled with it, carried outward from our sun in a constant stream called the solar wind. This plasma flows around Earth's magnetic field, sculpting our protective magnetosphere. When some of it leaks into our atmosphere, it creates the breathtaking spectacle of the auroras, the northern and southern lights. It's plasma, putting on a light show for us. Even the incredibly tenuous material between galaxies, the intergalactic medium, isn't empty. It's a vast ionized plasma, and it turns out it's the largest single component of ordinary visible matter in the entire universe. So, in a very real sense, we live inside a plasma universe, even though we can't see it with our naked eyes. So how do scientists even begin to describe something so complex and dynamic? They use a framework called magnohydrodynamics, or MHD for short. It's a brilliant marriage of two fields: fluid dynamics, study of how liquids and gases flow, and electromagnetism, the study of electric and magnetic forces. MHD treats plasma as a single, electrically conductive fluid. This allows us to understand how plasma can carry powerful electric currents, generate its own magnetic fields, and even self-organize into incredible structures. This is why we see plasma forming beautiful, glowing filaments in nebulae or massive arcing loops on the surface of the sun. It's the same physics at play in laboratory experiments here on Earth. Space isn't just a random, chaotic void. It's patterned. The electromagnetic interactions within plasma act like invisible strings, pulling matter together, shaping entire galaxies, and powering colossal jets of energy that shoot out from the vicinity of supermassive black holes. When you look at the universe through the lens of plasma physics, it transforms into a kind of grand electric sculpture, where magnetic fields and charged currents are just as fundamental to its structure as gravity itself. In physics, every state of matter exists because of a balance of forces, not a solid. Atoms are locked into a rigid structure. On a liquid, they are bound by cohesion but can flow past one another. In a gas, they are defined by random, chaotic motion. But plasma is different. Plasma is bound by energy. It's energy in motion, guided and sculpted by electromagnetic fields that can span billions of light years. This makes it the most energetic and dynamic form of matter in existence. Think about it. Every flash of lightning in a storm, every powerful solar flare erupting from the sun, every single star you see in the night sky, and every glowing nebula where new stars are born, all of these are manifestations of plasma's restless energy. Even nuclear fusion, the very process that powers the stars and creates the elements necessary for life, can only happen in a plasma. It's only in this superheated state that atomic nuclei can be smashed together with enough force to overcome their natural repulsion and fuse, releasing immense amounts of energy. So, in the end, what is plasma? It's the beginning of the universe. It's the heart of the stars. It's the invisible medium that fills the cosmos. Plasma is the state where the universe truly comes alive. It's not just the fourth state of matter. It's the state where matter becomes energy, and energy becomes structure. Look up at the sun. What do you see? A glowing ball of light, right? But what you're really seeing is the most powerful plasma machine in our cosmic neighborhood. That fiery surface crackles with energy, launching arcs of fire thousands of kilometers into space. These aren't just gentle curves of gas. They are plasma, a supercharged state of matter, twisted and sculpted by invisible magnetic fields under immense pressure. These are solar flares and coronal mass ejections, and they're a vivid reminder that our solar system isn't built on stillness, but on electric fury. The sun's core is a fusion reactor, a sea of charged particles where hydrogen atoms are crushed into helium, releasing the energy that sustains all life on Earth. But the real magic happens above the surface. In the sun's outer atmosphere, the corona temperatures inexplicably soar to millions of degrees, far hotter than the surface below. For decades, this was a mind-bending puzzle. The answer lies in a violent process called magnetic reconnection. Imagine invisible magnetic field lines twisting tighter and tighter until they snap and reconnect, unleashing the energy of a billion hydrogen bombs in a single flash. This is what powers a solar flare. This plasma violence blasts a continuous stream of charged particles out into space, the solar wind. It's not a gentle breeze. It's a relentless current carrying the sun's magnetic field with it, creating a vast bubble around our solar system called the heliosphere. This bubble is our shield. It's protecting us from harsh cosmic radiation and defining the boundary between our home and the vastness of interstellar space. The solar wind is the sun's electric fingerprint, stretching far beyond the orbit of Pluto. When this stream of solar plasma finally reaches Earth, it slams into our planet's magnetic shield, the magnetosphere. While most of it is deflected, so particles get funneled down along the magnetic field lines toward the north and south poles. There. They collide with atoms in our upper atmosphere, forcing them to glow. The result? The breathtaking auroras, the northern and southern lights. These shimmering curtains of green, red, and violet aren't just a pretty light show. They are visible plasma physics, a real-time ballet showing the epic struggle between our planet's magnetic field and the sun's electric fury. But this dance isn't always gentle. During intense solar storms, these interactions can become destructive. In 1859, the Carrington event, a massive solar storm, induced such strong electric currents that telegraph wires sparked and caught fire. Power grids can be knocked out, and satellites can be disabled. It's a stark reminder that plasma storms happening 150 million kilometers away on the sun can have very disruptive consequences right here on Earth. But this electric story doesn't end with our solar system. Zoom out, way out, and you'll see that plasma defines the very architecture of the universe. Modern telescopes reveal that entire galaxies are connected by enormous filaments of plasma stretching across. This cosmic web isn't just a collection of gas clouds. It's a network of ionized, magnetized streams that act like cosmic highways, guiding the flow of matter and feeding galaxies with the material they need to grow and evolve. Where these filaments intersect, we find galaxy clusters, the most massive and energetic structures in the cosmos. X-ray and radio telescopes have shown that these cosmic crossroads are filled with superheated, magnetized plasma. This plasma emits a special kind of light called synchrotron radiation, a dead giveaway that charged particles are spiraling through powerful magnetic fields. This tells us that magnetism isn't just a local phenomenon. It's a cosmic force, weaving an invisible magnetic tapestry through every galaxy, every cluster, and the vast voids of intergalactic space. At the heart of many galaxies lurk supermassive black holes. They are surrounded by accretion disks, swirling whirlpools of plasma heated to billions of degrees. But black holes don't just consume everything. They often launch colossal jets of plasma that shoot out at nearly the speed of light, extending for thousands of light-years across space. These jets are like cosmic particle accelerators, focused and guided by powerful magnetic fields. They are a spectacular example of one of plasma's most defining traits: its ability to self-organize into stable, coherent structures, even on immense scales. This filamentary nature is a hallmark of plasma, seen everywhere from tiny lab experiments to the majestic nebulae captured by the Hubble Space Telescope. Across the entire electromagnetic spectrum, from radio waves to X-rays, the universe is broadcasting the fingerprints of plasma. We detect synchrotron radiation from electrons spiraling in magnetic fields and Bremsstrahlung radiation from particles colliding. These signals are like cosmic Morse code, telling astronomers that plasma and magnetism are not just side notes in the story of the universe. They are fundamental drivers of cosmic evolution. Even the auroras on other planets, like Jupiter's powerful light shows or Saturn's ethereal glows, confirm the same universal principle. Wherever you find motion, charge, and magnetism, plasma takes center stage. Whether it's the ethereal glow of a nebula, the rhythmic pulse of a pulsar, or the cataclysmic shockwave of a supernova, plasma is the engine driving the spectacle. Supernova remnants, like the famous Crab Nebula, are expanding clouds of ionized material, their tangled filaments glowing brightly with synchrotron radiation. Inside the hyperdense cores of neutron stars, plasma currents generate magnetic fields 1 trillion times stronger than Earth's, creating objects known as magnetars. Even in the quietest-looking regions of space, invisible plasma turbulence shapes how energy and matter move, influencing everything from the birth of stars to the grand evolution of galaxies. So when you look at the cosmos, don't just see a collection of stars and galaxies held together by gravity. See a dynamic, electric ecosystem. Gravity gathers the raw material, but it's electromagnetism, acting through plasma, that organizes it, sculpts it, and gives it structure. It creates the filaments, loops, and arcs that make the universe look less like a random collection of objects and more like a living, interconnected web of energy. The 20th century gave us Einstein's universe of gravity and space-time, but the 21st century is revealing a complementary and equally profound truth. We live in a plasma universe, where electricity and magnetism are just as essential to the story of creation. As we continue to trace these electric threads across the cosmos, profound new questions arise. If plasma truly dominates the visible universe, how much of its behavior are we still missing? Could electromagnetic forces be far more significant on cosmic scales than we've ever imagined? Perhaps the universe isn't just a gravitational playground, but an interconnected electric network of fields and currents, humming with a power we are only just beginning to understand. We've seen it in every corner of the universe, from the sun's fiery surface to the farthest galaxies, glowing like ethereal ghosts, luminous filaments, nebular arcs, and lightning-like structures spanning between stars. It's plasma, the fourth state of matter. But beneath these beautiful discoveries lies a deeper question. Have we underestimated the role of electricity and magnetism in shaping the cosmos itself? For over a century, astronomy has been dominated by gravity, the great, silent architect of the universe. Yet nature's most energetic events, solar flares, galactic jets, and cosmic rays all arise from electromagnetic forces which are millions upon millions of times stronger than gravity. Could it be that our picture of the universe is missing a crucial piece? Let's look at this tale of two forces. Gravity is weak, but it's universal. It patiently shapes stars, planets, and galaxies. It pulls things together, slowly but surely. Electromagnetism, on the other hand, is incredibly powerful, but usually acts locally. It pushes and pulls only where electric charge exists. Here on Earth, in most ordinary matter, positive and negative charges cancel each other out, hiding this force's true cosmic potential. But in plasma, the game changes completely. The balance shifts. Electrons are stripped from their atoms, and charges move freely. This creates electric currents. These currents generate magnetic fields. And on a cosmic scale, these fields can stretch for light years, sculpting entire regions of space. Suddenly, we re-enter a realm where the laws of electromagnetism, Maxwell's equations, play just as big a role as Einstein's gravity. The idea that plasma might be fundamental to the universe's structure isn't new. It emerged in the early to mid-20th century with physicists like Hans Alfvén, Krasdian Birkeland, and Anthony Parrott. They began to suspect that electric currents flowed through space on scales far larger than anyone had imagined. Alfvén, a Swedish Nobel laureate, was a key figure. He proposed that magnetic fields and plasma interactions drive much of the cosmic activity we observe. His groundbreaking work in magnetohydrodynamics, or MHD, helped explain how plasmas move and how magnetic fields are generated and sustained in space. But he also issued a warning. He felt that astrophysics had become overly gravitational, treating plasma as just hot gas, instead of recognizing its powerful electrical nature. His ideas became the foundation of what some call plasma cosmology, or the electric universe, a controversial but fascinating perspective that asks if we can better understand the cosmos through electricity. Long before satellites, a Norwegian scientist named Krasdian Birkeland was already probing plasma's cosmic influence. In the early 1900s, he made a bold proposal: the beautiful auroras. The northern and southern lights were caused by charged particles from the sun traveling along Earth's magnetic field lines. Now call these Birkeland currents. At the time, his idea was dismissed. The common belief was that space was an empty vacuum, and magnetic fields simply couldn't extend that far. But decades later, satellites proved Birkeland was right. The auroras are, in fact, powered by vast electric currents that connect Earth to the sunny electrical circuits spanning millions of kilometers. This discovery completely changed how we see our solar system, not as isolated planets orbiting a star, but as electrically connected worlds within a massive plasma system. Hans Alfvén took Birkeland's insight and scaled it up to the entire galaxy, envisioned the universe as a vast network of cosmic circuits. In this view, electric currents generate magnetic fields, and those magnetic fields, in turn, guide the currents in self-sustaining loops. He suggested that galaxies aren't just held together by the gravity of dark matter halos, but are also shaped by electromagnetic structures, enormous plasma filaments, carrying current through intergalactic space. This was a radical idea, and it remains controversial today. Mainstream cosmology attributes the shapes and clustering of galaxies to the gravitational pull of dark matter, not giant electric currents. But as our telescopes get better, the conversation is reopening. We're now detecting magnetized filaments stretching between galaxies. Are these just magnetic leftovers from structures formed by gravity? Or are they active electrical currents, shaping galaxies through plasma interactions? The truth may lie somewhere in between, a hybrid cosmos where gravity gathers the matter, but electricity sculpts it into the structures we see. Modern instruments have revealed compelling evidence that supports at least part of this electric framework. Radio telescopes like LOFR and Meerkat have mapped enormous magnetic filaments spanning millions of light-years threads of plasma connecting entire galaxy clusters. The Planck satellite detected a faint polarization in the cosmic microwave background, afterglow of the Big Bang caused by intergalactic magnetic fields, suggesting that magnetism has been present since the very early universe. Meanwhile, spacecraft like the Parker Solar Probe and Solar Orbiter are flying right through plasma, directly measuring its flows and witnessing magnetic reconnection events. They re-showing that electric fields shape the solar wind and the sun's corona in ways far more intricate than we ever thought. Still, there's a limit to what we can measure directly. Space is vast, and detecting the faint electric fields across cosmic distances is incredibly difficult. Their large-scale effects often show up as magnetism, not as a clear separation of charge. But the patterns keep repeating wherever we look: filaments, currents, and magnetic ropes. The fundamental geometry of plasma seems to be universal. This brings us to a key unsolved mystery. Where did all this cosmic magnetism come from? Magnetic fields are literally everywhere in galaxies, in the space between stars, and even in the great cosmic voids. But magnetic fields can only be generated by moving charges by electric currents. What created the very first currents? One popular idea is the cosmic dynamo effect, where motion in conductive plasma amplifies tiny seed fields over billions of years. But that just pushes the question back. Where did the seed fields come from? Some theories propose they originated during the inflationary epoch right after the Big Bang, when quantum fluctuations in the early plasma were stretched across the universe. Whatever the source, magnetism appears to be ancient, possibly as old as the universe itself. And since magnetism can only exist because of electric currents, it means electricity, too, may have been a fundamental force from the very beginning. The debate between gravity and electromagnetism is often misunderstood. It's not about one force replacing the other. Mainstream cosmologists argue that while electromagnetism dominates local environments like stars and nebulae, gravity still rules on the largest scales where matter is mostly neutral and electrical forces cancel out. Proponents of the electric universe counter that plasma instabilities can allow charge separation and electric currents to persist across immense distances, playing a much larger role than standard models admit. The truth is likely a fusion of these extremes. Astrophysicists increasingly recognize that electromagnetism is not an optional extra in cosmic modeling. From magnetic fields guiding the birth of stars, to plasma jets influencing the evolution of entire galaxies, electromagnetism is an inseparable partner to gravity, not a replacement for it, but a co-author of the cosmic story. This merging of perspectives is reshaping modern astrophysics. Where earlier generations saw a cold, inert universe governed only by gravity, we now see a dynamic, charged cosmos, crackling with plasma flows and woven together with magnetic threads. Today, plasma research is a frontier of science, spanning from laboratory experiments to intergalactic modeling. In fusion reactors, scientists study plasma confinement to harness the power of the stars here on Earth. Supercomputers run massive simulations to model plasma turbulence from the sun's corona to galactic filaments. Yet plasma remains notoriously complex. It's dynamic and self-organizing. Tiny changes can trigger vast, unpredictable instabilities. It almost behaves like a living system, one we are still learning to understand. Beyond astrophysics, plasma might even help unify our understanding of fundamental physics. Some theorists believe that plasma behavior in the early universe could explain some of the deepest cosmic mysteries. From the origin of magnetic fields to anomalies in the cosmic microwave background, the study of plasma touches the deepest questions we can ask. How did structure emerge from chaos? How does energy organize itself into form? What invisible forces truly shape the cosmic order? From the vastness of galactic plasma to the delicate streams that paint auroras in our skies, one thing is clear: we are not separate from this electric universe. Our planet, our technology, and even our survival depend on how we interact with the plasma that surrounds us. It's a hidden ocean of energy, and its story is our story. It's easy to think of plasma as something distant, the domain of stars, nebulae, and galaxies. But in truth, plasma is here, surrounding us, shaping the space our planet moves through. It connects the sun to the Earth, and the Earth to the greater cosmic environment. We live quite literally in an electromagnetic cocoon, sculpted by plasma. The Earth is a magnetic planet. Its molten iron core acts like a dynamo, generating a magnetic field that extends tens of thousands of kilometers into space. This field forms a protective bubble called the magnetosphere, an invisible fortress that shields our atmosphere and surface from the harshest solar radiation. But the magnetosphere isn't static. It's alive, constantly shifting. It's a vibrating structure of plasma interactions between the Earth and the sun. As the solar wind, a stream of charged particles from the sun, flows outward, it encounters Earth's magnetic field. The result is a complex dance of forces, shock fronts, plasma waves, and field lines that stretch and snap under pressure. The outer boundary, known as the bow shock, is where the solar wind first slams into Earth's magnetic shield. Beyond it lies the magnetosheath, a turbulent region where solar and terrestrial plasmas mix. Inside, plasma spirals along magnetic field lines toward the poles, feeding the auroral ovals, the very zones where the magnetosphere connects directly to our atmosphere. These regions form a global electrical circuit. Energy flows from the solar wind into Earth's magnetic field, down to the atmosphere, and back into space again. Our planet is not isolated. It's part of an interplanetary plasma circuit, between roughly 60 and 1,000 kilometers. Above us lies the ionosphere, a region of the upper atmosphere where sunlight ionizes gas molecules, turning them into plasma. This layer is crucial to modern civilization. It reflects and refracts radio waves, allowing long-distance communication. It also influences GPS signals, satellite links, and space weather. The ionosphere constantly changes, pulsing with the day-night cycle. It's flaring during solar storms and responding to the shifting patterns of the magnetosphere. During intense geomagnetic storms, currents surge through this layer, causing auroral substorms and even affecting electrical systems on the ground. These ionospheric currents, or Birkeland currents, were first proposed more than a century ago. Today's spacecraft have directly observed them as glowing plasma ropes connecting the upper atmosphere to the magnetosphere. They are, quite literally, electric cables linking Earth to space. Even within our atmosphere, plasma makes dramatic appearances. Lightning, one of nature's most powerful phenomena, is a plasma discharge. When electric charge builds up in storm clouds, the potential difference becomes so great that the air itself breaks down into plasma, allowing current to flow. A single lightning bolt can heat the air to over 30,000 degrees Celsius, creating plasma channels that emit radio waves, gamma rays, and even antimatter in the form of positrons. But lightning doesn't stop at the clouds. Above thunderstorms, high in the stratosphere and mesosphere, lie mysterious transient plasma events, sprites, elves, and blue jets, glowing structures that reach toward space, linking weather systems to the ionosphere. These discoveries remind us that Earth's atmosphere isn't purely meteorologic. It's electromagnetic. Every flash of lightning echoes the plasma processes that occur on stars, scaled down to our own sky. In the age of electricity, this hidden ocean of plasma has a direct impact on our lives. We depend on satellites, power grids, and global communications, all vulnerable to plasma disturbances. When powerful solar flares or coronal mass ejections erupt from the sun, they hurl vast quantities of charged particles toward Earth. If one of these strikes the magnetosphere, it can compress the magnetic field and trigger a geomagnetic storm. These storms induce currents in electrical systems, sometimes strong enough to overload transformers and cause blackouts. This happened during the March 1989 Quebec blackout, when a solar storm left millions without power. High-altitude flights can experience increased radiation, GPS accuracy can drop, and satellites can suffer electrical discharges that disable their systems. The sun's plasma storms, once distant spectacles, are now a planetary hazard. That's why space agencies around the world, NASA, ESA, JXA, and others, continuously monitor the sun's plasma output to predict and mitigate these effects. Interestingly, the Earth itself produces plasma. In the upper atmosphere, cosmic rays and solar ultraviolet light constantly ionize air molecules, creating a thin but persistent layer of charged particles. This plasma layer interacts with Earth's magnetic field to form global current systems, like the equatorial electrojet, a continuous current circling the planet's magnetic equator. Even the quiet sun produces constant plasma variations that drive this system, meaning that our weather, our magnetosphere, and our daily radio communications are all influenced by the electric pulse of the cosmos. And deep underground, within the conducting layers of the Earth's crust, these space-driven electrical variations can induce currents capable of subtly affecting pipelines, cables, and even geological processes. It's a humbling realization. The Earth's systems are not closed. They're open, responsive, and electrically connected to the rest of the solar system. Our understanding of plasma isn't just theoretical, it's practical. Plasma is everywhere in modern life. Plasma TVs and neon lights use controlled discharges to produce light. Semiconductor manufacturing relies on plasma etching at microscopic scales. And space travel is being revolutionized by plasma thrusters, like ion drives, which use electromagnetic acceleration instead of combustion. These technologies are only the beginning. As scientists learn to control plasma more precisely, the boundary between natural plasma phenomena and engineered plasma systems continues to blur. We're beginning to replicate on a small scale the very forces that shape the cosmos. Every second, the sun sends millions of tons of plasma into space. Some of it drifts harmlessly by, but a portion is always interacting with Earth's magnetic field, charging our radiation belts, illuminating our skies, and affecting our environment. This ongoing exchange, called space weather coupling, means that the Earth and the Sun form a single, dynamic system, a magnetically connected pair. Space probes like NASA's magnetospheric multi-scale mission have revealed that energy transfer between the solar wind and our magnetosphere happens through magnetic reconnection, the same plasma process that powers solar flares. In this way, the Earth's magnetic field breathes, compressing and expanding, flaring and relaxing as solar plasma interacts with it. We are, in essence, participants in a cosmic plasma circuit that stretches from the Sun's surface to the edge of the solar system. Even life itself is not entirely removed from plasma phenomena. The ionosphere influences the chemistry of the upper atmosphere, including the formation of ozone, crucial for shielding life from ultraviolet radiation. Cosmic plasma interactions may even have played a role in the early Earth's environment, affecting atmospheric electricity and possibly influencing the chemistry that led to the origin of life. And today, lighting a plasma process helps fix nitrogen from the atmosphere, making it available for plants. Without plasma, the biosphere itself might be very different. When we step outside on a clear night and look up at the stars, it's tempting to imagine that we are surrounded by emptiness. But every particle of space around our planet is part of a living electric system. From the aurora above our poles to the plasma streaming from the sun, we are connected not just gravitationally, but electromagnetically to the universe beyond. As our instruments reach farther into this electric ocean, humanity's understanding of plasma continues to evolve. Did you know that most of the visible universe is made of something we can't even see? It's not solid, not liquid, not gas. It's plasma, an invisible ocean of charged particles that fills the space between stars and galaxies. For most of human history, it was a complete mystery. So, how did we go from complete ignorance to mapping this cosmic ocean? This is the story of how humanity unveiled the electric skeleton of the universe. Our journey begins not in space, but right here on Earth, in the labs of the late 19th and early 20th centuries. Scientists like William Crookes were playing with electricity, sending it through glass tubes filled with low-pressure gas. What they saw were beautiful, glowing patterns, sparks, and arcs. They didn't know it yet, but they were creating miniature plasmas. These glowing tubes, known as Crookes tubes, were the ancestors of our old CRT televisions. Then, in 1897, J.J. Thomson discovered the electron. Suddenly it clicked. These glowing discharges were made of charged particles, the very building blocks of plasma. Around the same time, a brilliant Norwegian scientist named Christian Birkeland had a wild idea. He believed the stunning northern lights were caused by electrical currents flowing from the sun. To prove it, he built an incredible experiment called the Tendrils. It was a magnetized sphere, a mini-Earth inside a vacuum chamber. He shot a stream of electrons at it and amazingly recreated the auroras in his lab. His theory was controversial at the time, but he was right. Birkeland had laid the groundwork for space plasma physics long before we could even send a rocket into orbit. The true revolution, however, kicked off with the space age. Before satellites, scientists could only guess what was happening above our atmosphere. They knew something up there was messing with radio signals and they saw the auroras, but there was no direct proof. That all changed in 1958 with the launch of Explorer 1. This little satellite made a startling discovery. Earth is surrounded by intense bands of trapped, charged particles, what we now call the Van Allen radiation belts. For the first time, we had touched the plasma that fills space. Following this, missions like Pioneer and Voyager ventured deeper into the solar system. They encountered something incredible, a constant stream of plasma flowing outward from the sun, called the solar wind. And this wasn't just a smooth, uniform flow. It was a turbulent, structured river of particles, guided by invisible magnetic fields that stretch across the entire solar system. This interplanetary magnetic field, or IMF, acts like a cosmic highway system, shaping the magnetic environments of all the planets, including our own, driving the phenomenon we call space weather. But what about plasma beyond our solar system? To see that, We needed different kinds of eyes. Radio telescopes allowed astronomers to detect something called synchrotron radiation. This is light produced when superfast electrons spiral around magnetic field lines. By mapping this radiation, we could suddenly see glowing plasma filaments inside the explosive remains of dead stars. And powerful jets of plasma being shot out from the centers of distant galaxies. We were mapping the invisible structure of the cosmos. Then came X-ray observatories like Chandra. They revealed vast clouds of incredibly hot gas lurking between galaxies in massive clusters. This gas, heated to tens of millions of degrees, is pure plasma. It's completely invisible to regular telescopes but shines brightly in high-energy X-rays. Theory had predicted it, but now we could see it. The universe, it turned out, was threaded with electrically active structures, some spanning millions of light-years. The cosmic web wasn't just a concept, it was real, and it was made of plasma. While astronomers looked to the stars, physicists on Earth were trying to tame plasma in the lab. They built incredible machines called tokamaks, and stellarators donate-shaped magnetic bottles, designed to contain plasma heated to temperatures hotter than the core of the sun. The goal: to achieve nuclear fusion, the same process that powers the stars, and create a clean, nearly limitless source of energy. These experiments also allow us to study fundamental plasma behaviors like turbulence and magnetic reconnection, in a controlled setting, helping us understand the dramatic events we see happening on the sun and across the universe. Today, we're in a golden age of plasma exploration. Missions like the Parker Solar Probe are literally touching the sun, flying through its outer atmosphere, the corona, and directly sampling the plasma there. The Solar Orbiter is giving us unprecedented 3D views of the sun, revealing the complex dance of its magnetic fields. Closer to home, missions like Themis and MMS are studying Earth's own magnetosphere in incredible detail, watching in real time as energy from the solar wind is funneled into our atmosphere to create the auroras, just as Birkeland predicted over a century ago. These missions confirm that plasma is anything but passive. It's a dynamic, self-organizing force that can unleash incredible amounts of energy. Our understanding of plasma has moved from the purely theoretical into our everyday lives. Plasma propulsion is now being used to power spacecraft on long journeys, using ionized gas to create efficient thrust. In industry, plasma is used for everything from etching the microscopic circuits in your smartphone to sterilizing medical equipment. It's a powerful tool that demonstrates how mastering this fundamental state of matter is not just an academic pursuit, but a new technological frontier. The story of plasma is a perfect example of human curiosity. From those first glowing tubes in a Victorian lab to spacecraft flying through the sun's fire, every step has brought us closer to seeing the unseen. We've discovered that the universe is woven together by a vast flowing network of energy and charge. This journey is far from over. It forces us to ask, if this plasma ocean connects everything, what does that mean for our future? Can we harness it for energy, for travel between the stars? As humanity prepares to expand into the solar system, how will our destiny be shaped by this electric cosmos? For centuries, we saw the universe as a vast, empty void, dotted with stars and planets held together by gravity. But we were missing most of the picture. As our view sharpens, we're discovering that space isn't empty at all. It's filled with a hidden ocean, a dynamic sea of charged particles and magnetic fields. This is the plasma universe. For ages, it was an invisible concept, a distant curiosity. Today, it's the new frontier of human exploration. As we look to the stars, plasma offers not just understanding, but incredible possibilities. The power to propel our spacecraft to other worlds, to reshape planets, and even to influence the cosmic structures around us. Think about how we travel in space now. Traditional rockets are basically controlled explosions, burning massive amounts of chemical fuel for thrust. But the universe itself works differently. Stars and colossal cosmic jets harness the power of plasma, using electromagnetic forces to accelerate charged particles. And now, humanity is learning to do the same. We're building plasma propulsion systems. You might have heard of ion thrusters, like the one that powered NASA's Dawn spacecraft on its years-long mission to Vesta and Ceres, demonstrating incredible fuel efficiency. Then there are Hall effect thrusters, which are already widely used on satellites for precise maneuvering, creating high-speed plasma flows. But the real game changers are on the horizon. Experimental engines like VASIMART, the Variable Specific Impulse magnetoplasma, rocket promise to/interplanetary travel times. Imagine a trip to Mars taking weeks instead of many months. Plasma propulsion isn't just about going faster. It's about being smarter and more efficient. We're learning to tap into the same fundamental physics that drives solar winds and galactic jets. In a way, we're finally learning to ride the universe's own electric currents. Beyond just getting around, plasma could become a tool for cosmic engineering on a planetary scale. Could we manipulate Earth's magnetosphere to shield us from devastating solar storms? Could we create plasma shields to protect astronauts on long journeys to Mars and beyond? What about stabilizing the orbits of asteroids or even deflecting comets that pose a threat to our planet? This isn't just science fiction anymore. Experiments in labs and tests in space are hinting that engineering with plasma might one day be possible. The biggest challenge, of course, is scale. Earth's plasma environment is vast, turbulent, and incredibly complex. But with every new breakthrough, from fusion research in tokamaks to new ion thrusters in orbit, we get one step closer to wielding plasma as a powerful tool. Looking even further into the future, plasma could unlock nearly limitless energy. Fusion reactors, which are essentially stars in a jar, aim to replicate the sun's power source here on Earth by controlling plasma. Some scientists are even exploring concepts like magnetically confined collectors that could harvest energy directly from solar flares or the solar wind. And for interstellar travel, ideas like magnetic sails could use plasma interactions with the interstellar medium to push spacecraft across the light years between stars. All of these concepts are inspired by the mechanisms already at work across the cosmos. By decoding the secrets of plasma, we're essentially learning the universal toolkit that stars, nebulae, and entire galaxies use to move, create energy, and organize themselves. The truth is, plasma is already a fundamental part of our technological civilization, whether we realize it or not. Our global communication systems rely on reflecting radio waves off the ionosphere, which is a layer of plasma in our upper atmosphere. Satellites have to constantly navigate the complex interactions between magnetic fields and plasma to stay in orbit. Even our power grids on the ground are vulnerable to geomagnetic currents caused by plasma storms from the sun. As humanity ventures deeper into space, our reliance on understanding plasma will only grow. Our survival and our expansion across the solar system will depend on our ability to read, predict, and ultimately manipulate the plasma environment around us. This leads to some incredible, almost fantastical ideas about astroengineering. Could we one day use controlled plasma currents to stabilize or even create atmospheres on other planets? Could we build plasma deflection systems to reliably protect Earth from asteroid impacts? Could our descendants build plasma-powered megastructures, shaping magnetic fields and energy flows on a cosmic scale? While it sounds speculative, it's all grounded in physics we can observe. The universe itself showcases these principles, with plasma jets, filaments, and magnetic ropes that stretch for thousands of light years. By learning to control plasma, humanity is aligning itself with the fundamental currents that shape the cosmos. This exploration forces a profound shift in how we see everything. The universe is not a silent, empty stage. It's a dynamic ocean of charged particles, a living network of energy and currents. Gravity may provide the skeleton, but it's plasma that brings the universe to life. Stars, planets, and galaxies aren't isolated islands. They're all nodes in a vast, interconnected electric web. In understanding this hidden ocean, we gain more than just scientific knowledge. We gain a new sense of our place within a living, charged cosmos. We are both observers and participants in this cosmic dance. Every shimmering aurora, every satellite's path, every experiment in our labs echoes the forces that have shaped the universe since the beginning of time. This brings us to the ultimate questions. Can humanity learn to harness the immense power of plasma responsive for clean energy, for rapid propulsion, and for planetary protection? Can we navigate this electric cosmos safely, understanding its turbulence and its subtle structures? And perhaps most profoundly, if plasma connects everything, how does that reshape our view of ourselves and our place in this universe? The hidden ocean is vast, complex, and humming with power. It is a frontier that is both scientific and existential, a challenge to our minds, and an invitation to explore, innovate, and connect with the cosmos in ways our ancestors could only dream of. Plasma is the fourth state of matter, the electric heartbeat of the universe, and we are no longer just watching from the shore. We are becoming explorers of the electric universe. Thank you for joining us on this journey. If you found this as fascinating as we do, don't forget to like this video, subscribe to our channel, and hit that notification bell so you don't miss our next deep dive into the cosmos. See you next time.